Hello, everyone. Today we are going to talk about the most mysterious phenomenon in the universe, black holes. Stay tuned. It is going to be fascinating.
Black holes are among the most extraordinary objects the universe has ever created. And as you explore their story, you begin to realize that they are not simply exotic cosmic monsters, but profound expressions of the deepest laws of nature. They sit at the edge of what physics can describe, tearing open the boundary between what you know and what you can only imagine. Understanding black holes means understanding the nature of gravity, the structure of space-time, the behavior of information, and perhaps even the birth of new universes. And so your journey begins not with destruction, but with creation. Black holes are born, just as stars are born, and their birth tells you everything about how the universe shapes itself. A black hole begins with a star, but not just any star. It must be a star with a mass far greater than that of your sun. These massive stars live fast and die violently. For millions of years, they burn hotter and brighter than any normal star, fusing hydrogen into helium, helium into carbon, carbon into oxygen, and so on, building heavier and heavier elements within their hearts. All the while, their intense fusion reactions push outward, resisting the star's own gravity that constantly tries to crush it inward. This delicate balance, gravity pulling in, fusion pushing out, is what keeps the star alive. But the balance cannot last. Eventually, the star exhausts its nuclear fuel. When the fusion stops, the outward pressure vanishes. Gravity wins, and the core collapses. The collapse is catastrophic. In a fraction of a second, the inner core shrinks dramatically. Temperatures rise to unimaginable extremes. In some cases, this collapse triggers a supernova, a titanic explosion that blows the outer layers of the star into space. But the core continues falling inward, crushed by its own weight. If the core is heavy enough, nothing can stop its descent. Not even the pressure of neutrons, not even quantum physics. The collapse becomes unstoppable, and the star's core becomes a black hole. The moment a black hole is born is the moment a boundary forms, the event horizon. This is not a physical surface like the crust of a planet. It is a region of space-time where escape becomes impossible. If you approach the horizon from the outside, you can still escape if you accelerate hard enough. But once you cross it, nothing you do will ever carry you back. Not even light can get out. The event horizon is the ultimate point of no return. Inside the event horizon, all paths lead inward, deeper into the gravitational well. The geometry of space-time becomes so twisted that every direction points toward the core. There is no stable orbit, no turning back, no fight. Crossing the event horizon is not like falling into a cave or sliding down a slope. It is more like crossing into a region where the very meaning of direction changes. At the center of every black hole is the singularity, the point where the equations of general relativity break down. The singularity is not necessarily a physical object. It is a place where your current understanding of space-time ends, a region where density becomes infinite, where curvature becomes infinite, where all familiar concepts fail. But even the idea of a singularity may not be a final answer. It might simply be where Einstein's equations stop being valid, and where quantum gravity must take over. In that sense, the singularity is a boundary not only in space, but in knowledge. It is the edge of what physics can currently describe. Yet black holes are not simple. They come in many varieties. A non-rotating black hole is described by the Schwarzschild solution to Einstein's equations. A rotating black hole is described by the Kerr solution, and it is far richer and stranger. Around a Kerr black hole is a region called the ergosphere, where space-time is dragged around by the black hole's rotation. In this region, nothing can remain still. Everything must rotate with the black hole. This phenomenon, known as frame dragging, shows you that space-time is not passive. It moves, it swirls, it flows like a fluid under intense gravity. Inside the ergosphere, energy can be extracted from the rotation of the black hole. This is the Penrose process, a remarkable idea proposed by Roger Penrose. It means that black holes can, in principle, be tapped for energy, although the practical challenge is immense. Rotating black holes also produce some of the most powerful jets in the universe, narrow beams of plasma that shoot from the regions near their poles at speeds close to that of light. These jets can extend for thousands of light years. They shape galaxies. They ignite star formation. They sculpt the cosmic web. In many ways, black holes are not destroyers. They are cosmic engines. But the most profound mystery of black holes is not their birth or their structure. It is the fate of information. In physics, information means the precise quantum state of matter. When matter falls into a black hole, what happens to the information describing it? Does the information vanish? If so, that means information can be destroyed, violating one of the most fundamental rules of quantum mechanics. Stephen Hawking discovered that black holes are not entirely black. They emit radiation, now called Hawking radiation. This radiation arises because the vacuum is never truly empty. Virtual particle pairs constantly appear and annihilate near the event horizon. In some cases, one particle falls in while the other escapes. To conserve energy, the black hole must lose a tiny bit of mass. Over time, the black hole shrinks. Eventually, after an almost unimaginable period, the black hole evaporates completely. But what happens to the information that fell in? Does the information disappear with the black hole? Hawking initially believed so. But this creates a paradox. The loss of information violates quantum mechanics. It suggests that the universe is not predictable at its deepest level, that something fundamental is broken. Many physicists believe information must escape somehow. Perhaps it is encoded in the Hawking radiation itself. Perhaps the event horizon is not smooth, but filled with quantum structure. Some propose the existence of a firewall, a region of intense energy that destroys anything crossing the horizon, eliminating the smooth crossing predicted by general relativity. Others propose that the event horizon acts like a hologram, storing all information on its surface. According to the holographic principle, everything inside a volume of space can be described by information encoded on its boundary. In this view, a black hole is not truly a three-dimensional object. It is a two-dimensional information storage device. A more radical idea comes from the concept known as ER equals EPR. This proposal suggests that entangled particles linked by quantum correlations are connected by tiny wormholes known as Einstein-Rosen bridges. If this idea is correct, then a black hole evaporating into Hawking radiation becomes a vast network of tiny wormholes connecting the interior to the radiation outside. Information is preserved, but in a deeply non-classical way. At this point, your understanding of black holes begins to shift. They are no longer simply regions from which nothing escapes. They are quantum laboratories where the deepest principles of the universe are tested. And yet, the mysteries continue. If you were to fall into a black hole, what would you see? From the outside, you would appear to slow down, your light becoming redder and dimmer as you approach the horizon. To an external observer, you never quite cross it. But from your own perspective, you would cross the event horizon without noticing anything unusual. The horizon is not a wall, it is simply a region defined by geometry.
Inside, things change quickly. If the black hole is small, tidal forces, differences in gravitational pull across your body would stretch you into a thin filament, a process known as spaghettification. But in a supermassive black hole, the tidal forces at the horizon are gentle. You could cross it without harm, only to be crushed later near the singularity, where the curvature becomes extreme. What happens in the final moments is unknown. It is where classical physics fails and quantum gravity must take over. Perhaps the singularity does not truly exist. Perhaps the matter rebounds. Perhaps the interior opens into another region of space-time. This leads to white holes, theoretical opposites of black holes. A white hole is a region that matter can leave but never enter. White holes appear in certain mathematical extensions of the equations describing black holes. They have never been observed. But some theories suggest that black holes may turn into white holes in their final stages, exploding outward as they evaporate. Another idea proposes that the interior of a black hole may be connected to another universe. If the singularity is not a point but a bridge, then every black hole could contain a new expanding region of spacetime. In this view, black holes are cosmic wombs. They birth universes with different laws of physics. And your own universe may have been born in the heart of a black hole from a parent universe long gone. If black holes can give rise to new universes, then the cosmos itself may be a vast branching structure. Each universe might produce countless black holes, each black hole giving birth to new universes, each universe evolving its own physical laws. In such a cosmic family tree, your universe may be only one generation in a lineage extending far beyond anything you can observe. This idea is known as cosmological natural selection. In this framework, universes that are more effective at producing black holes generate more offspring. Over many generations, universes evolve, becoming increasingly optimized for black hole formation. And remarkably, the physical constants of your universe, values that seem astonishingly fine-tuned to allow stars, galaxies, and life, are the same values that maximize the production of massive stars which later collapse into black holes. This coincidence is striking. If the constants of physics were even slightly different, black holes might be far less common. Perhaps your universe appears fine-tuned for life only because it is fine-tuned for black holes, and life is an unexpected bonus produced along the way. But before exploring the cosmic genealogy further, you must examine the detailed structure of black holes in more depth. A black hole is defined above all by its horizon. The event horizon marks the boundary at which escape becomes impossible. But there are other horizons. A rotating black hole contains an outer horizon and an inner horizon. Between them lies the ergosphere, where space-time is dragged around so violently that rotation becomes unavoidable. Inside the inner horizon, the laws of physics behave unpredictably. The geometry is unstable to even small disturbances. In many simulations, the inner horizon becomes a region of intense energy known as mass inflation, where the curvature becomes enormous. But in some theories of quantum gravity, the inner horizon stabilizes, opening into another region of spacetime. This inner region may resemble a tunnel, a wormhole, or even a bounce into a new universe.
The idea that the interior of a black hole connects to another region of spacetime is not as speculative as it sounds. The original Schwarzschild solution describing a black hole contains two asymptomatically flat regions connected by a wormhole, a bridge known as the Einstein-Rosen bridge. This bridge collapses too quickly for anything to cross it. Yet rotating or charged black holes have more complex interior structures. Their geometries contain pathways that, mathematically, lead to other universes. Whether these pathways survive quantum effects remains unknown. As you travel deeper into the mathematics, you encounter a profound truth. Black holes are not simply objects. They are solutions to the equations of general relativity. They are geometries. They are shapes carved into spacetime by mass and energy. And these shapes reveal the deepest relationships between gravity, motion, and time. For example, when an object falls toward a black hole, it does not simply move through space. It moves through a geometry shaped by the black hole's mass. From the perspective of an outside observer, the object appears to slow as it approaches the horizon, its light stretched to longer and longer wavelengths. But from the perspective of the falling object, nothing unusual occurs at the horizon. Time continues normally. The difference is not a contradiction. It is a difference in perspective. Time near a black hole flows differently depending on where you are. This difference in time flow has dramatic consequences. Near the horizon of a supermassive black hole, time passes more slowly relative to regions farther away. A few minutes near the horizon might correspond to hours, years, or centuries in the outside world. This is not science fiction. This is general relativity in action, and it has been confirmed repeatedly by experiments, satellites, and observations of stars near the center of the Milky Way. Speaking of the center of the Milky Way, it contains a supermassive black hole known as Sagittarius A star. Its mass is roughly 4 million times that of the Sun. Stars orbit around it at incredible speeds, following the predictions of Einstein with astonishing accuracy. Observations made with the Event Horizon Telescope in recent years revealed a glowing ring of light surrounding the dark interior, the first direct image of a black hole silhouette. The ring is not the horizon itself, but the region where photons orbit the black hole, creating a bright, distorted image of the surrounding gas. This is the photon sphere, a place where light can circle the black hole before escaping or falling in. The Event Horizon Telescope also produced an image of a much larger black hole at the center of the galaxy M87, which is billions of times more massive than the Sun. The image revealed a glowing, halo-like structure around the dark interior, confirming predictions made decades before. The fact that humans have captured images of black holes is one of the greatest achievements in science. It is as if you have photographed the shadow cast by the laws of nature themselves. But even these observations do not reveal the whole truth. Much of a black hole remains hidden. You can observe only what happens outside the event horizon. The interior remains forever concealed. Yet there are indirect ways to probe the interior. When two black holes collide, they emit gravitational waves, ripples in the fabric of space-time. These waves carry information about the shapes and motions of the black holes during their final orbits and merger. Detected for the first time in 2015 by the LIGO Observatory, gravitational waves opened a new window into the universe. Each gravitational wave signal is like a voice. It tells you how massive the black holes were, how fast they were spinning, and how violently they collided. These waves travel across billions of light years, undisturbed by matter, giving you a pristine picture of the event. As more detectors come online, you will be able to listen to the universe with increasing sensitivity. You will detect collisions involving black holes of different sizes, different spins, different histories. You may detect the mergers of primordial black holes formed moments after the Big Bang, or collisions involving exotic objects like boson stars or dark matter halos.
Black holes serve as the ultimate laboratories for testing the limits of general relativity. When two black holes collide, the gravitational field becomes so strong that it pushes Einstein's equations to their extremes. If relativity fails anywhere, it will fail here. But so far, every collision observed has matched the predictions of general relativity with extraordinary precision. Einstein's theory remains unbroken. Yet general relativity cannot be the final word. It does not include quantum physics. It cannot describe what happens at the singularity. It cannot resolve the information paradox. And so physicists seek a deeper theory, one that merges quantum mechanics and gravity. One candidate is loop quantum gravity. In this theory, space-time itself is quantized. It is made of tiny loops of geometry, forming a network called a spin foam. According to loop quantum gravity, the singularity inside a black hole is replaced by a bounce. Instead of collapsing into infinite density, the matter reaches a minimum size and then expands again. The interior of the black hole becomes the seed of a new region of space-time. This is one of the strongest mathematical arguments for black holes containing new universes. Another approach comes from string theory. In this framework, elementary particles are not point-like but tiny vibrating strings. The vibration pattern of a string determines its mass and charge. String theory naturally includes gravity and predicts extra dimensions of space. In this context, the singularity of a black hole becomes a region where the usual notion of space-time breaks down and the extra dimensions become relevant. The interior may open into another region or another universe. A more radical idea proposes that space-time is not fundamental at all. Instead, it emerges from quantum entanglement, the invisible correlations between particles. In this picture, the geometry of space-time is created by patterns of entanglement. If the entanglement changes, the geometry changes. The interior of a black hole becomes a manifestation of entanglement between the interior and the exterior. This is related to the idea that wormholes or Einstein-Rosen bridges are equivalent to entanglement itself. This ER equals EPR idea is one of the most remarkable developments in modern theoretical physics. It suggests that quantum entanglement creates space-time, and black holes, being the most entangled objects imaginable, may serve as the foundation stones of space-time itself. If this is true, then black holes are not the edges of space-time, they are the engines that build it. Black holes also raise deep questions about time. Inside a black hole, time and space exchange roles. The direction that once represented movement through space becomes a direction through time. The singularity is not a place in space, but a moment in time. Once you pass the event horizon, you are moving inevitably toward the singularity as surely as you move toward the future in your ordinary life. Time inside a black hole has only one direction. And yet, if the singularity is replaced by a bounce into another universe, then the arrow of time may reverse on the other side. The collapse of one region could be the expansion of another. The end of time in one universe could be the beginning of time in the next. This brings you back to the idea of black holes as cosmic seeds. If every black hole contains a newborn universe, then your universe may have originated from the collapse of a massive object in a previous cosmos. The Big Bang would be the daughter universe emerging from the interior of a parent universe's black hole. In this framework, universes reproduce, they evolve, they vary. They form a multiverse with structure, lineage, and inheritance. Black holes become the reproductive organs of the cosmos.
If black holes truly create new universes, then each universe inherits the physical laws of its parent, but with slight differences. These differences determine how many stars it will produce, how long those stars will live, how many black holes will form, and whether complex structures such as galaxies, planets, and perhaps even life can emerge. Over cosmic generations, universes that produce more black holes give rise to more offspring universes. This is the essence of cosmological natural selection. It suggests that your universe, with its seemingly fine-tuned constants, may be the product of countless generations of cosmic evolution. But even if black holes do not literally give birth to new universes, they remain central to the story of the cosmos. They shape galaxies, they drive the growth of cosmic structure, they power quasars, some of the brightest objects in the universe, and they regulate star formation. Without black holes, galaxies would look completely different. They might not form stable structures at all. The universe you know would be impossible. Consider the supermassive black holes found in the centers of galaxies. The black hole at the center of galaxy M87 is billions of times more massive than the Sun. It fires jets of particles across thousands of light years. These jets influence the gas in the galaxy, heating it, compressing it, and triggering or suppressing star formation. In many galaxies, black holes act as cosmic thermostats, controlling the temperature and composition of interstellar gas. Your own Milky Way contains a supermassive black hole at its center, surrounded by stars that orbit at extraordinary speeds. By observing these stars, astronomers have verified Einstein's predictions about gravity with remarkable precision. The motion of these stars reveals the mass of the black hole, the geometry of space-time around it, and the way time behaves under extreme gravity. And yet, the black hole itself remains invisible. You cannot see the horizon. You can only see the effects of the black hole on nearby matter. Gas falling into the black hole forms an accretion disk that glows brilliantly from friction and magnetic turbulence. This disk emits light across the electromagnetic spectrum, from radio waves to X-rays. The structure of the disk reveals information about the black hole's spin, mass, and magnetic field. But the closer you get to the horizon, the stranger the physics becomes. Near the horizon of a rotating black hole, space-time twists like a whirlpool. Time slows, space deforms, light bends. Photons travel in orbits around the black hole, creating the bright ring seen by the Event Horizon Telescope. This ring is the shadow of the black hole cast against the glowing gas. The fact that humanity has captured this shadow is nothing short of miraculous. You have photographed not a surface, not an object, but the absence of light, the boundary where light disappears forever. You have seen the edge of the unknowable. Of all the mysteries surrounding black holes, none is deeper than the question of information. Physics is built on the idea that information cannot be destroyed. Yet black holes appear to destroy information by swallowing it. Hawking radiation complicates the picture even further. It suggests that black holes evaporate, leaving no trace of what fell in. If the black hole evaporates entirely, what happens to the information? This paradox has shaped theoretical physics for decades. It has led to profound insights that have reshaped your understanding of space-time. One insight is that the event horizon may not be empty. It may be filled with quantum structure, storing information in a way that is invisible to classical observers. Another insight is that the interior of a black hole may be connected to the exterior through quantum entanglement. The Hawking radiation emitted by the black hole may be entangled with the interior, preserving information in a subtle and non-local way.
If the holographic principle is correct, then everything that falls into a black hole is encoded on its surface. The interior becomes a representation of that information. In this sense, the black hole is a hologram. It contains an entire volume of space-time encoded on a two-dimensional boundary. This idea extends beyond black holes. It suggests that the entire universe may be holographic. Everything you see, everything you know may be encoded on a cosmic horizon far larger than you can imagine. Space-time itself may be a projection, emerging from a deeper layer of information. In this framework, black holes become the key to understanding the origin of space-time. They are windows into the quantum fabric of the universe. They are the places where gravity and quantum mechanics meet. They are the boundaries between the known and the unknown. Inside a black hole, the rules of physics change. Space becomes time. Time becomes space. Movement becomes inevitable. This inversion of roles challenges your intuitive understanding and forces you to confront the relativity of all physical concepts. If time can become space, what else can the universe transform? This question leads you back to the idea of wormholes, tunnels through space-time that link distant regions. The classical Einstein-Rosen bridge collapses too quickly to allow travel, but quantum mechanics may stabilize wormholes under certain conditions. A wormhole might not be a passage you can travel through physically, but a link between entangled particles. According to the ER equals EPR conjecture, entanglement is wormholes. Wormholes are entanglement. The geometry and the quantum information are two sides of the same reality. In this picture, the universe is woven from a vast network of entanglement. When entanglement changes, space-time changes. Black holes are simply the densest knots in this network. They are regions where entanglement becomes so intense that it curves space-time into a closed region. Another frontier of black hole research comes from the idea of firewalls. The firewall hypothesis proposes that the smooth crossing predicted by general relativity is wrong. Instead, there may be a region of extreme energy at the event horizon that destroys any object entering the black hole. This idea attempts to solve the information paradox, but at the cost of abandoning a fundamental principle of relativity, that falling through the horizon should feel like falling through empty space. Whether firewalls exist remains uncertain, but the debate reveals how deeply black holes challenge your understanding. Every assumption you make about space,
time and information must be tested. Black holes demand new physics. Yet black holes are not only laboratories for theoretical physics. They are also engines of cosmic evolution. When black holes merge, they release gravitational waves that ripple through the universe. These waves carry energy, momentum, and information about the event. The mergers may seed new black holes, create even larger black holes, or shape the dynamics of galaxies. Supermassive black holes play a critical role in galaxy formation. Without them, galaxies might collapse or fail to develop stable spiral structures. Black holes regulate star formation, preventing galaxies from becoming too dense or too diffuse. They influence the rotation curves of galaxies, the flow of gas, and the formation of clusters. They shape the cosmic web, the vast network of filaments and voids that spans the universe. Black holes also raise profound philosophical questions. What does it mean for information to be preserved? Does the universe need observers to define reality? Is space-time fundamental, or is it an emergent phenomenon? Are black holes doors to other regions of the universe? Are they the birthplaces of new universes?
These questions lead you to the ultimate frontier, the origin of the universe itself. If black holes can create new universes, then the Big Bang may be the birth of your universe from a black hole in another. The constants of physics may be the inherited traits of a cosmic parent. Inflation may be the echo of a collapse. The arrow of time may be the memory of a bounce. In this view, the universe is not a single event, but part of an infinite chain of creation. Each universe gives birth to others. Each universe inherits the laws of its ancestors. And each universe evolves. Black holes are the storytellers of this cosmic genealogy. They reveal the unity of gravity, quantum physics, information, and geometry. They show you that the universe is far stranger, deeper, and more interconnected than your senses suggest. As your journey through the story of black holes comes to an end, remember this: every atom in your body was once inside a star. Some of those atoms may one day fall into a black hole. And perhaps, far in the future, those atoms will help seed a new universe. The story is never finished. It continues endlessly across cosmic time. Black holes are not the end. They are the beginning of something greater. The story of the universe did not end with black holes. In many ways, that story was only the preface. Once you have followed matter into the abyss of a singularity, once you have watched space-time twist itself into impossible shapes, you begin to understand something profound. The cosmos contains far stranger structures, deeper mysteries, and more astonishing facts than anything you have imagined so far. And many of these wonders do not lie at the bottom of black holes. They fill the universe around you. As you step beyond the horizon of what is known, you discover that the cosmos is not simply large, it is structured, layered, and unbelievably diverse. The universe is not a random scattering of stars. It is an interconnected system shaped by physics, time, and ancient processes that began long before the Earth existed. So let us continue our journey. Let us explore the lesser-known truths of the cosmos, the facts that scientists rarely discuss in documentaries, the ones that reveal how mind-bending the universe truly is. And as before, imagine you are guiding your viewer through the darkness, a cosmic narrator illuminating the unknown. The universe is not just big, it is structured like a giant living organism. People often say the universe is unimaginably large, but size alone is not its most mysterious quality. What truly sets the cosmos apart is its structure. Matter arranges itself in patterns that resemble neurons, river systems, blood vessels, and lightning bolts. This is not poetry, this is observation. Astronomers use massive surveys to map galaxies across billions of light years. And what they find is a network known as the cosmic web. It consists of enormous filaments of dark matter,
clusters of galaxies glowing at the nodes, vast voids spanning millions of light years, rivers of gas feeding galaxy formation. If you place an image of the cosmic web next to an image of the human brain, the similarity is astonishing. Both structures distribute information and matter through filamentary networks. Both follow mathematical rules of optimization. Both evolve, one biologically, the other cosmologically. Does this mean the universe is alive? No. But it does mean that complexity emerges naturally at every scale of reality. The same mathematics governs the flow of neurons and galaxies. The same principles sculpt matter into repeating patterns. It is as if the cosmos is telling you, the laws of nature repeat because they are universal. The universe creates time, but time also shapes the universe. You were taught to imagine time as a straight line, but in cosmology, time is a shape, curved, stretched, twisted, and even accelerated. Its flow depends on gravity, motion, and temperature. One of the strangest discoveries of modern physics is that the early universe experienced time differently. A trillionth of a second after the Big Bang may contain more events than an entire billion-year era later. Time does not pass uniformly. It stretches like fabric. And here is a fact that many people never hear. Time flowed slower in the past because the universe was denser. Galaxies were closer. Dark matter was compact. Radiation filled every direction. The early universe was so hot and thick with energy that the passage of time was dramatically different from today. This is one reason why astronomers can look billions of years into the past simply by pointing a telescope upward. Light itself moves through the layers of time like sediment. Every galaxy you see is a message from the past delivered across unimaginable distances. The universe is mostly invisible, and we still do not know what it is made of. You live in a universe where ordinary matter equals about 1/20th of all matter. Dark matter, the majority of mass. Dark energy, the majority of everything. That means 19 out of 20 particles around you are not atoms. They are not electrons. They are not protons. They are not anything you can touch. The cosmos is built from invisible ingredients that do not emit light and rarely interact with anything. But here is the strange part. Dark matter might not be a particle at all. Most people heard the standard explanation: unknown particles drifting through galaxies shaping gravity. But some physicists suggest radically different possibilities. Possibility 1. Dark matter is made of primordial black holes. Tiny black holes born during the Big Bang. They would be everywhere, invisible but detectable through gravitational lensing. Possibility 2. Dark matter is a new state of matter. Not particles, but a type of cosmic fluid occupying the large-scale structure of the universe. Possibility 3. Gravity itself behaves differently on cosmic scales, meaning the universe might not contain dark matter. You may simply be using the wrong equations. No matter which idea is correct, the implication is the same. You live inside an invisible ocean. Everything you see is a thin mist floating inside a much greater hidden world. The beginning of the universe may have been colder than you think. People imagine the Big Bang as the hottest moment in history. That is true, eventually. But some cutting-edge models suggest something surprising. Before the hot Big Bang, the universe may have been cold, very cold. In the bounce models of cosmology, the universe existed before the Big Bang in a contracting state. As gravity squeezed space-time, temperatures dropped. Only when contraction reached a critical point did energy surge, triggering the fireball that created light elements. This means the Big Bang might not be the absolute beginning. It might be a transition from one cosmic era to another. And if the universe can collapse and rebound, then time may be cyclic. Universes may be born from previous universes. The Big Bang may be one chapter in an infinite cosmic story. Some physicists believe the universe has died and been reborn countless times. Each rebirth erases most information, but leaves behind subtle fingerprints, patterns in the cosmic microwave background, anomalies in curvature, unexplained asymmetries. A universe with memory. The cosmos may be full of impossible objects. Black holes were once considered impossible, then they were discovered. Now scientists suspect the universe contains a whole family of exotic objects that defy classical physics. 1. Boson stars. Hypothetical stars made entirely of quantum particles that obey completely different rules. They would be transparent, almost ghost-like, and could mimic the gravitational signature of black holes. 2. Quark stars. Objects denser than neutron stars, containing free quarks, the building blocks of protons and neutrons, dissolved into a strange soup.
3. Naked singularities. Regions where gravity is so extreme that the singularity is not hidden behind a horizon. These would break general relativity. 4. Gravastars. Structures formed by vacuum energy, where the interior repels matter instead of attracting it. None of these objects have been observed directly, but the equations allow them, and the universe has a habit of turning mathematics into reality. Space is not empty, it is boiling with quantum fluctuations. The vacuum looks empty, but it is anything but empty. On the smallest scales, particles constantly appear and disappear. Energy flickers in and out of existence. Virtual particles form, collide, annihilate, and reform. This restless quantum foam fills every cubic centimeter of space. In fact, the vacuum contains more energy than every star in the universe combined. But we do not feel this energy directly because it is evenly distributed. Only when the vacuum changes slightly near black holes, inside early universe inflation, or in certain quantum states does its power become visible. Some physicists believe the expansion of the universe is driven by vacuum energy. Others think vacuum energy is the source of multiverse creation. In certain models, universes bubble out of the vacuum like foam on the surface of an ocean. And you, the observer, exist inside one of those bubbles. As you travel farther into the cosmic landscape, you begin to understand that the universe is not only stranger than you imagine, it is stranger than you can imagine. Every time scientists believe they have reached the limits of what is possible, a new discovery tears open a deeper layer of mystery. Your cosmic journey expands into realms where common sense breaks apart, where extremes of temperature, density, and gravity create phenomena unlike anything on Earth. And the farther you go, the more the universe reveals one truth: reality is not what it seems. Let us continue. The universe has a hidden architecture you can only see through gravity. Light tells you only a fraction of the cosmic story. Most of what exists does not shine. It does not reflect. It does not absorb. It passes through the cosmos like a shadow through fog. The only way you can detect it is by watching how it bends space-time. Astronomers discovered entire structures made of nothing. Enormous concentrations of dark matter forming the skeleton on which galaxies hang. You can map these structures only by observing gravitational lensing, the bending of light as it travels past massive objects. Here is one of the most astonishing facts. Some of the largest known structures in the universe are invisible. Colossal walls of dark matter stretching across hundreds of millions of light years. Vast filaments thicker than galaxy clusters. Enormous halos holding galaxies together like cosmic glue.
Without dark matter, the stars would fly apart, galaxies would disintegrate, and cosmic structure would not exist. The visible universe is only a decoration placed atop a hidden mass distribution. In this sense, the universe has two layers: the luminous layer, made of atoms, the structural layer, made of dark matter. And the structural layer dominates. Gravity is not a force. It is the shape of reality. You grow up imagining gravity as a force, something like a cosmic magnet. But in general relativity, gravity is not a force. It is the geometry of space-time. Everything you do, walking, jumping, falling, is a conversation between your mass and the shape of space-time. The Earth bends space-time. You move along the curvature. You do not feel gravity pulling you. You feel the ground pushing you upward because it stops your free fall. This is why astronauts in orbit are weightless. They are not floating because there is no gravity. They are weightless because they are falling continuously around the Earth. And here is the deeper truth. Gravity is the only reason time itself exists in different shapes. Time flows slower in strong gravitational fields. It flows faster in empty, flat regions. Place a clock at sea level and another at the top of a mountain. The one at the mountain will tick slightly faster, measurable and real. Even your phone's GPS would be off by miles if it did not correct for gravitational time dilation. That is how deeply gravity is woven into the structure of reality. Galaxies spin too fast, and no one can fully explain why. When scientists measure the rotation of galaxies, they find something impossible. Stars on the edges spin just as fast as stars near the center. Gravity from visible matter is not strong enough to hold them together. Galaxies should tear themselves apart.
But they do not. Two explanations exist. Explanation 1, dark matter forms giant halos around galaxies. Invisible mass providing the missing gravitational pull. Explanation 2, the laws of gravity may be different at large scales. This idea is known as modified Newtonian dynamics. It suggests gravity behaves differently in low acceleration environments. Both explanations fit observations. Neither explanation has been proven. The universe is leaving you clues and daring you to understand them. Some galaxies are almost entirely dark. Astronomers have found galaxies with almost no visible matter. They are made almost entirely of dark matter, with only a sprinkling of stars. Others are the opposite, huge, ghostly galaxies with almost no dark matter at all. This variety reveals something profound. The universe is far more diverse than a simple model of dark matter predicts. Something else is shaping galaxies, something you do not yet understand. The universe contains stars that defy logic. Most people imagine stars as giant glowing spheres of hydrogen, but the cosmos builds stars from extremes. Here are some of the strangest. 1. Hypergiants, the brightest stars in the universe. Stars like Eta Carinae radiate millions of times more energy than the Sun. They live fast, die young, and explode with unimaginable violence. 2. Neutron stars, the densest objects short of black holes. A teaspoon of neutron star matter weighs as much as a mountain. Their magnetic fields are trillions of times stronger than Earth's. 3. Magnetars, monsters born in supernovae. These stars emit flares that can wipe out electronic systems across vast distances. A magnetar burst detected on Earth once affected the upper atmosphere despite being 50,000 light-years away. 4. Rogue stars, moving through space alone. Some have been kicked out of galaxies during collisions. They drift in intergalactic darkness for billions of years. The diversity of stars is a reminder. The universe is a cosmic laboratory full of experiments still running. Nearly all matter in the universe is from stars that died long ago. Every atom in your body was forged in a star. Carbon from giant stars, oxygen from supernovae,
iron from collapsing cores. But here is what people rarely understand. Many of the atoms in your body were forged in stars that no longer exist. The universe is a recycling system. Every supernova enriches space, and every new generation of stars inherits the chemical elements created by older stars. You are literally made of cosmic history. The most powerful explosions ever recorded are not supernovae. Supernovae are enormous, but they are not the most extreme events. Two greater titans exist. One, gamma-ray bursts. These are colossal jets of energy shooting from collapsing stars or neutron star mergers. For a few seconds, a gamma-ray burst can outshine an entire galaxy. Two, fast radio bursts. Millisecond-long flashes of radio waves coming from distant galaxies. Some repeat, some do not. No one knows exactly what causes them. A single fast radio burst can release more energy in 1 millisecond than the sun emits in 100 years. Think about that. 1,000th of a second versus 100 years. The universe does not merely create explosions, it creates impossibilities. The universe may have directions you cannot see. You live in a three-dimensional world: length, width, height. Time is the fourth dimension, but many theories suggest the universe contains extra dimensions, curled up, hidden, tiny. String theory requires at least 10 dimensions. Some models propose 11. Others propose infinite dimensional structures. These dimensions may be microscopic, curled up so tightly that you cannot interact with them.
But they influence everything: particle properties, the strength of forces, the nature of gravity, the evolution of the universe. If you could see these extra dimensions, the universe would look entirely different. Some physicists believe black holes may reveal the extra dimensions because their gravity is so extreme that hidden dimensions may stretch or unfold. And remember, if an extra dimension exists, it also has geometry. And if it has geometry, it has physics. The universe you see may be only a shadow of a higher dimensional reality. We are still only scratching the surface. Ви просили продовження на 30 000 символів, і ета примерно друга треть. Готов двигатись далі. As you reach the far edge of the cosmic frontier, you begin to understand something profound. The universe is not simply a place, it is a process. It is a story. It is an engine of transformation, endlessly reshaping itself from one state to another. Everywhere you look, the cosmos is changing. Galaxies merging, stars forming, planets colliding, particles creating new structures. In this final part of our journey, you will explore the most astonishing truths of all. Facts that even many scientists rarely speak about. Truths that redefine what the universe is. Let us continue. The universe is filled with impossible temperatures. When people imagine the cosmos, they often think of cold emptiness. But the truth is far more extreme. The universe creates temperatures that defy imagination, both hot and cold. The hottest places. The hottest known temperatures exist not in stars, but in particle accelerators. When two heavy nuclei collide at nearly the speed of light, they create quark-gluon plasma, a state of matter hotter than the entire universe was moments after the Big Bang. This plasma reaches temperatures of more than several trillion degrees. That is hotter than anything in nature. The coldest places. The coldest naturally occurring region in the universe is the Boomerang Nebula. Its temperature 1 degree above absolute zero. How does a cloud of gas get colder than empty space? Because it expands so quickly that it chills itself, like the universe did during its earliest moments. But here is the twist. Humans have created even colder temperatures. In some laboratories, scientists have cooled atoms to billions of a degree above absolute zero.
colder than the Boomerang Nebula, colder than cosmic background radiation, colder than anywhere nature has achieved. At those temperatures, atoms behave like a single quantum wave. Matter becomes collective, like a single giant particle. In those labs, you are not just studying the universe, you are recreating conditions that may have existed before the first stars. The universe has a horizon, a limit to what you can ever know. There is a boundary in the cosmos you can never cross. It is called the cosmic horizon. Light takes time to travel. The universe has existed for only a finite amount of time, so you can see only as far as light has had time to reach you. Right now, the cosmic horizon is more than 40 billion light-years away, even though the universe is only about 14 billion years old. Why? Because space itself has expanded, pulling distant galaxies away faster than light can cover the growing distance. This leads to one of the strangest facts about reality. There are galaxies you can see but can never reach, even at the speed of light. Their light comes to you, but nothing you send can ever reach them. They are beyond your causal influence, beyond your reach forever. Even stranger, there are regions of the universe you will never see at all. Light from them will never reach Earth. Not in 10 trillion years. Not ever. Those regions may contain galaxies, civilizations, or structures unlike anything you will ever know. The universe is bigger than what you observe. Much bigger. The cosmos may have no center and no edge. One of the most counterintuitive truths is that the universe may not have a center. Imagine a balloon being inflated. Each point on the surface sees every other point moving away. There is no central point on the balloon's surface. The center is outside the surface in another dimension.
Likewise, the universe may be expanding in a higher dimensional space. You are inside the fabric, not observing it from the outside. Even stranger, the universe may have no edge. If you traveled in a straight line long enough, you might eventually return to your starting point. Not because the universe is closed like a sphere, but because geometry can curve in ways your intuition cannot grasp. Space can be finite yet unbounded. Just like the surface of Earth, finite area, no edges. The cosmos is mostly empty, but this emptiness has structure. People imagine space as an endless void. But the emptiness is not simple. Between galaxies lie cosmic voids spanning tens of millions of light-years. These are the largest structures in the universe, vast spheres nearly devoid of matter. Yet these voids are not truly empty. They contain traces of gas, rare galaxies, dark matter filaments, leftover radiation. Some cosmologists believe voids hold crucial clues to dark energy. Because with so little matter to interfere, the expansion of space in voids reveals the pure behavior of dark energy. Voids may be the quiet laboratories of the universe. The universe creates cosmic islands beyond which you can never travel. As expansion accelerates, galaxies move away faster and faster. Over enormous timescales, this leads to cosmic isolation. Eventually, every galaxy cluster will become an island universe. All distant galaxies will fade beyond the horizon. Only your local group will remain visible. Future astronomers, billions of years from now, will see only a small cluster of galaxies and may never know the universe once contained trillions. Humanity lives in a privileged cosmic era. You were born early enough to see the universe while it is still visible. The universe produces sound, but not the way you think. Sound requires a medium, and space is mostly empty. So people assume the universe is silent. But the early universe was filled with dense plasma. In that plasma, sound waves rippled through space, compressing matter. These sound waves shaped the distribution of galaxies you see today. They left a faint imprint known as the baryon acoustic oscillation, a fossil sound wave frozen into the cosmic structure. If you could hear those waves scaled to human frequencies, the universe would have had a deep, resonant hum, a cosmic heartbeat. The universe may be quantized, like pixels in a cosmic screen. Some theories propose that space is not continuous. It is granular, like pixels. Each pixel of space is unimaginably small, the Planck length, 1 decimal point followed by 34 zeros, then a 1. You cannot observe these pixels directly, but their consequences may appear in black hole physics, quantum gravity, early universe fluctuations, the holographic principle. If the universe is quantized, then space-time is not the stage, it is a product. Not the container, but the result. The cosmos becomes a computation. Physics becomes information. The universe is not static, it evolves on every scale. Galaxies collide and merge. Stars are born and destroyed. Atoms form, break apart, and reform. But even constants may evolve. Some studies suggest that the fine structure constant, which determines the strength of electromagnetism, may vary slightly across the cosmos.
If true, this means physics is not identical everywhere. The universe may have regions with different versions of chemistry, gravity, or light. This does not break science, it deepens it. The universe creates beauty as an emergent property. From a scientific perspective, beauty is often dismissed as subjective. But cosmic beauty is objective in one sense. The most complex structures arise where order and chaos meet. Galaxies spiral because gravity organizes chaos into harmony. Nebulae glow because dying stars enrich space with heavy elements. Rings around planets arise from collisions and gravitational tides. Beauty is not an accident. It is a consequence of physics optimizing itself. The universe may be one of infinite versions of reality. The multiverse is not science fiction anymore. It is a serious scientific concept. There are several types. 1. The inflationary multiverse. Eternal inflation creates infinite bubble universes. 2. The quantum multiverse. Every quantum event branches into new realities. 3. The string theory landscape. Different vacuum states produce universes with different laws. 4. The black hole multiverse. Each black hole contains a new universe inside. 5. The geometric multiverse. Different regions of space-time have different dimensions, curvatures, or topologies. If any version is true, then the universe is not the universe. It is a chapter. The universe is full of questions that will outlive you. Despite all discoveries, the greatest mysteries remain. What is dark energy? What is dark matter? Why do physical constants have their specific values? Are we alone? What existed before the Big Bang? Why does the universe produce consciousness? Does time have a beginning, a direction, an end? Is reality fundamental or emergent? The universe is not finished. It is still unfolding, and you live inside its story.